In this video, we are going to begin our discussion of section 12.1, vectored value functions. So everything we've done in chapter 11, we'll now start applying to functions, and bear with me, but we're almost to the calculus. You may be wondering, we've actually taken a whole test, and there was 0 calculus on that test. Well, this is where it starts getting involved in the calculus with the vectors that we have been studying. So a quick reminder, we've done this semester, but just in case, in R2, if you're unsure what that R2 means, that means like two-dimensional space. Sorry for the zoom in there. Two-dimensional space, that's like what we studied so far through calculus, the x and the y direction, 2 dimensions. What we're doing now is we're trying to go to 3 dimensions, that's R3, just in case I've passed over that somehow. So in 3 space, we just have, instead of x and y, we have an x, y, and z. Right now, surprise, we have already done these this semester with lines. That's one of 2 ways to define a line, is through parametric equations. So let's recall what a vector function is going to look like, and we're not recalling, but in 3 space, they're defined as the vector as some x component, some y component, and some z component. For functions, we're going to do the exact same thing. We're going to plug in some value of t for our vectored value function, and we're going to get a vector out of this function, right? We'll plug in t, then we'll get this vector here, right? F of t, g of t, h of t, whatever those may be. That is not our function, though, not the set of vectors. What happens, let's look at a 2-dimensional case on the left here, the graph, is when we plugged in our first point, we got this vector here in orange, but the actual graph itself is the point. The vector points at the point that we are going to plot. So when we plug in the second one, t1, whatever that may be, we'll just call them 0 and 1 just to make sure it's easy. Plugging in 1, it goes a little further, gives us an orientation as well. The third vector I'd plug in, I'd get this vector as my answer, and that would give me my second value. And it just creates the curve. The vectors aren't part of the curve. They're creating and pointing at the curve. In 3 space, as you can tell on the right, it's the same exact way. It's just in 3 dimensions, so it's actually pointing into space instead of on the xy plane. The important part to note here is the orientation I did mention, but it does tell us a direction because the way it's defined, it makes sense that we have to plug in this vector and it's going to point at our next point. So it makes sense that it's going to show us which way the graph is moving. This is called a space curve or a vectored valued curve. We're going to call it a space curve a lot. We are going to be dealing with these space curves throughout the rest of the semester. It'll go away a little bit, and then it'll come back at the end with some really cool ideas at the end that I really love. So let's add to this idea. We're going to talk about these functions. Anytime we talk about a function, we have to talk about how to find its domain. What can we even plug in, right? Domain is things that we can plug in. So we have 3 functions here. We have f of x, that's my first x component. That's ln of t. I'm going to write these out because it helps me think about them. And it makes it very easy to write out. What I mean by this, there will be a test question that's like this. Probably. And I'm going to change this to the 1/2. This is clear work. For this now, I can take each one. I'm like, okay, the domain of ln of t. What we're going to find is we're going to find the domain of each part, and it's all the same t. Like each t here can't be a different t. Whatever I plug in, I have to plug into all 3 parts, the same t. So I need to make sure that I can plug it into all 3 parts. So what I need to do is find what can I plug into each part, and then figure out what would cover, what numbers will work for everything. So the domain for ln of t, if you don't remember that, I don't want to do the highlighter. We can't plug in 0, but we can plug in any positive number. The domain for g, right, that's 1 over t minus 2. The only thing we can't plug in here is 2, so it's negative infinity to 2, union with 2 to infinity. And then the last thing, that's a square root. I went ahead and changed it just out of habit. I guess we don't need to here. But the domain of this thing, I'm changing it back to square root, is, okay, I can plug in 0, because square root of 0 is 0, and then I can plug in all positive numbers. All right, so now I have all 3 of these domains. And like I said, Remember, the green highlighted t up there, when I plug something into this function, right, when I decide on a number to plug in, it has to go into each component. If it can't go into each component, you can't plug it into your vector. That just doesn't make sense. So you are trying to find what mapping, and you could do this. I've seen students do this thing. Okay, so here's f. Let's put some numbers. There's a 2 on here. So we'll do f in red. I've seen students do this. So, okay, that's here on. And then I'll do G in green. Okay, G is everything except for 2. And then we'll do H in blue, and that is a bracket here on forever. So you can tell, remember that this open circle here means it skips right over, or it's an open parentheses. So the only overlapping part, and we want all of it, well, we have right here, this is a parentheses as well. So we have all 3 of them fit into here with a parentheses and a parentheses. It won't work on bracket on that side because one of them has a parentheses. Then on this side, I have a parentheses, and they all exist going on that way. So I write down my domain. Okay, well, that is 0 to 2, union with 2 to infinity. This is the domain of our vector valued function. So again, what we did is we found what t's can we plug into each component, so f, g, h. Then we looked at those domains. We sketched it on a number line. If you can just think about it, that's great. I don't require the number line at all. It's just a visual for yourself. And then you can write down the domain of R of t because it's going to be what we call the intersection of those domains. So if we wanted to write that out, we could. Domain, zoomed in on me. Domain of R of t, that's my vectored value function, is going to be the intersection of the domain of x of t intersected, that's that, not union, but intersected with domain of y of t intersected with the domain of g of t. Oh, we called it h, shouldn't we? X, y. It was z would have made more sense, but we're here. So, oh, maybe I didn't call it. We'll call it z. You get the point. All right, so there's that, the domain for that. Let me fix this up real quick. There we go. So if you want to find the domain, we have 3 parts here, right? Domain of x intersected with the domain of y intersected with the domain of z. 3 different domains, we find where they overlap. All right, going on, we are going to start sketching these things. There's a way to approach this kind of graphing, so I'm going to help you out with doing that. First thing I would do every single time is identify each variable. Okay, x is root of t, and y is 2 minus t. Now, I can change this. This becomes, if I wanted to solve for a t, t would be equal to, well, to get rid of the square root, I would take x squared. Now I'm going to plug that into the t. So this goes here with this. I get y equals 2 minus x squared. All right, or you could think about it this way. Y equals negative x squared plus 2. That's in graphing form now. So we're going to go up 2 here. And then we know that it's going to, I'm actually going to extend this a little bit because I want a bigger picture. So we're going to do 2 there. And then we'll say everything this way. Each 2 marks will be 1. Okay, so my parabola crosses the x-axis at square root of 2. So we're going to get something like this. And I'm going to do it in a dotted line. Ooh, let me actually use their dotted line feature. It's nicer. So I get this parabola. Like something like that. Right? A little bigger than 1 because it's the square root of 2. There we go. Okay, the reason I did it in dotted line for a moment, and some of you are going to be like, oh, I wish I would have waited. Yeah, because we're going to fill some of it in. And it's actually, we didn't do much. But what we're looking at now is we're going to figure out where it is on this parabola. Because remember, it's a like vector pointing from the origin to a point, and then it keeps pointing at points telling you where to go on that curve. So what that means is I need to find where we're at t equals 0. So r equals 0 gets me the vector 0, 2. So that's this top point. It's already sketched in. So I'm going to do that. And then now I'm going to do t equals 1. And this is going to tell me where it goes next. So I plug in 1. I get 1, 1. All right, 1, 1's right here. So this tells me my curve goes this way forever. Right, with the t's going up. Doesn't go the other way. That's why we don't sketch the whole curve. The curve is not, let me fix that a little bit. The curve is not the dotted line. The dotted line just tells me where the curve could be. But once we fill it in, then we have a curve and a direction. So it starts at that, goes on that way. Not too bad. It's different than what we're used to. So first you have to do is take the x and y's and make an equation to see it. Graph that equation on a dotted line because that's where your curve possibly could be. Sometimes you're going to fill in the whole dotted line, which we will in this lesson. Sometimes you only do half of it like we did here. So the curve itself is the solid orange line starting up at 0, 2 and going down. Okay, let's get another example under our belt in 3 dimensions though. All right, so first thing we always do is write down our components. So x equals 2 plus t, y equals negative 2 minus t, z equals 1 plus 2t. Hopefully something's ringing in your head, right? Bells ringing, red flags. This is a line. So I have everything I need. Since I know it's a line in space, I still only need 2 points. So I'm going to start at t equals 0, plug that into my function. So we get the point 2, negative 2, 1. Okay, so we get the point PO, we'll call it 2, negative 2, 1. So let's plot that. 2 on the x, so out this way, negative 2 on the y. So I'm going to, how I do this is I like to, if you're doing this on paper, or you just grab a ruler. I don't have a ruler, so I'm going to do this. So negative 2 in the y. So we are, and then this one's got to be parallel to the y-axis. Straight across. So let's do dotted lines there. There we go. Sorry, thought I was writing and I wasn't. And I'm going to write one right on top of this line. And I can just take that line away. There we go. All right, that's 2 to the right, 2x, negative 2 in the y, and then 1 in the positive direction. So there is P. I was like, why does it look weird? Go up 1, and then we're going to put a point. There we go. I was still dotted when I was trying to make a point. So this is PO. Right, the next point, we just do t equals 2. You could do 1. I just want to make sure it's maybe spread out a little bit. So we get 4, 0, and 5. All right, so 4 in the positive direction for the y. And then I'm going to draw, this is my ruler. Make sure it's the same as that. Positive 4. And then we have a positive 4 in the y direction, so make my ruler here. Okay, so then I just go and I draw dotted lines. You'd be using a ruler. Thanks for your patience. There we go. Okay, so now I can just take these lines away. Delete, delete. There we go. Okay, and then it says it goes, oh, it wasn't 4 in the y, it was 0 in the y. Okay, so we don't need either one of those lines. So 4 in the x, we're out here, and then 5 in the y. So here's my length of 5. I can just go make a point, do a line. I'm going to take that line and move it here. 4 in the x, 0 in the y, and then we can go ahead and make that solid. There we go. Here is 0.1. And we know it goes from 0.1 or 0.0 to 0.1. They didn't give us any t's, so t's go off in both directions, and so we could just do a line that goes through both of those. It's going to miss, but I'll straighten it up. Oh, one sec. There we go. All right, so we just get a line in 3 dimensions. Kind of hard to see, but you can do your best to line up you'll have a ruler. Be a little easier than mine. So we have this line going on forever. We would start at P0 and only do like a ray going up if this said like t is greater than or equal to 0. But since it said nothing, we have to do it in both directions. But I do need to write the way it goes. It goes in this direction. Pretty neat. I would recommend on the notes, I'll try to remember to go back, and right now I think they're blank, but I'll go back and put these grids on there to help you out. I'm going to put those on any kind of graphing like this that shows up on test to help you out. I would recommend never sketching your own. You can. Mine always looks extremely bad when I try to sketch my own. So there's our line in 3 space. So what if it's not a line? The reason this was so easy in 3 space is we acknowledged that it was a line, and then we just found 2 points and connected them. We never wrote this, but maybe we should have. 4, 0, 5. We found our 2 points, and then we connected them in 3 space. Use a already made graph. Use a ruler. Remember, the whole point, or the key to graphing in 3 dimensions is using those axes as a reference. So, okay, let's do another one. All right, for this one, right, this one's a bit different. First thing we're going to do every single time is just go ahead and label each component. So we have them. And then what you're going to want to do is relate 2 of them to create, you'll see. So let's do this. It makes most sense to just, instead of writing y equals t squared, I can write y equals x squared, right? I can replace t with x because that's what that says. Okay, this is a cylinder, right, from last chapter, along z, with trace on x, y plane. Right, you can do, just so you know, you can get more than one surface from this. We could have done something else. I could have plugged in y for t squared and got z equals y, and then it turns into a different graph. There's not a correct way. What I typically go with is I go with what I know. Well, I know x squared. X squared is we do it so much in college algebra. You guys know this. We do it in calc. We do it in Calc 2. We use parabolas all the time. So using that tells me it's an easier surface for me to deal with. So let's write a couple notes here. The y equals x squared will give a surface. What I mean by surface is literally it's like a mountain range or a field with a little bit of hills and stuff over the top of this, right? Like a surface that's on top here. Some kind of surface. That will give a surface. And then the other function, z equals t cubed, will actually give us the space curve. Gives space curve. And this is on the surface. This is really neat, by the way. And you don't see it yet because we haven't started graphing it, but this is really neat. Cool way to graph technique. So let me get that line back up. There we go. All right, so first we're going to do is graph our cylinder. So y equals x squared. I'm going to do that in red. No, let's do it in green. Okay, so I have my x and my y, and y equals x squared. If I graph it, okay, so if I try to keep my best here, 1, 1, so we get some kind of parabola that looks like this. Right? I probably could have done a lot better. Let's see if I can. That'll work. Okay, so we have that, and then we actually have this little portion, and I'm going to go ahead and copy and paste it, because we're getting a cylinder. You would just draw this again, but it's at any point up and down. I'm going to make it look decent on here by doing the copy and paste thing. All right, paste again, because I'm going to put it at the bottom. All right, so we get this cylinder. Delete those spots. All right, and we get, if we run lines up and down, you can see the parabola itself being a three-dimensional shape, and I'll do a dotted line to cover the back there. But it is a parabola up and down, right? Three-dimensional shape, so we have this like folded over forever on one side, this point here, there. Hopefully you can see 3 dimensions. If you can't, I would advise you to go plug this into a three-dimensional grapher. Said 2 words, 1 sentence, weird. Plug that into your GeoGebra 3D or something like that. Make sure you understand that that's there. Now I know that z equals t cubed is part of my space curve, and it's going to be on top. It's literally going to be on that surface. So it's going to be walking along that three-dimensional surface. So how I figured that out is I start at time 0, wherever it started. The beginning said t starts at 0, t is greater than or equal to 0. And then plug that into my function, and we get the 0 vector. So that points at our vector. So I'm going to plot that. That is my first point on my curve. And then I'm going to go t equals, let's give us some room with 2. T equals 2, if I plug all that in. Okay, so I get 2, 4, 8. Okay, 2, 4, and then 8. All right, 8's way up here. So it's going to be something like that. And it's going to be going on that surface, and it's not going to backtrack like that, but it's going to be exponential because of that z value. But it's going to be on top of that green surface, so we have that folded over like surface there in green, right? Hopefully you can see it. And then the red line is living on the green surface. It's running, it starts there on top, on the very top, and it's like going downhill, but to the right. If you turn your picture on the side, maybe you can see it a little better. But it's a surface with that line running along the side of it. Hopefully you can picture that. If you're having a hard time picturing what these things should look like, let me know, or go check out your textbook. Actually, that's where I'm going to go grab it. Check out whatever ebook or textbook you're looking at. If you don't have one, Google this topic, and you'll find pictures of these space curves on top of these surfaces, so you can get a real image. I don't know if my 3D grapher will work with that since it's a vector function. But yeah, check that out. Check out some pictures to get some more interesting takes on these. Let's do another example over graphing our vector valued curves in 3 dimensions. So this is a common way to, maybe you didn't remember doing this in Calc 2, but we are going to create, given these parametric equations, so let's write those out. All right, and we can actually solve these for cosine and sine, and you'll see why I'm doing that. If you remember this from Calc 2, you're probably already ahead of me. So I divide both of those. All right, remember from trig, this thing just keeps resurfacing, it never goes away. This trig identity, it's Pythagorean trig identity. It says if I square both of them, add them together, I get a 1. So we're just going to replace that now. They get squared, right? Y squared, and then I square the 4 to get 16, and that equals 1. And that gives me my curve. And this is since we're missing the z component, it's a cylinder, right? Since we're missing z, along z axis, trace is in xy plane. So let's go ahead and trace that. Okay, so it's hopefully you see it. It's a cylinder. It's an ellipse, and it has 2 on the x-axis and 4 on the y-axis, right? And we get this ellipse. So something like this. I think I could do a little better than that, maybe. Sorry, iPad's being finicky. And I think it did worse, but I think I gave up. Okay, so there is that side of the ellipse. This side of the, I'm going to do the back side with the dotted line because we're not going to really supposed to be able to see it. Right, so we get some kind of cylinder that looks like up and down, right? So I'm going to draw a straight up and down line. I'll try to get it straight here. And then all right, so hopefully you can tell what this is. This is like your Pringles can or whatever you want to think about, anything that is a cylinder, right? That goes straight up and down. Actually, it's not a Pringles can because it's an ellipse, right? Most Pringle cans are circular until you squash them. All right, so there's what that looks like. You could even take that ellipse there that's in the middle, and we could put it, put it down here. Maybe that'll make it look better, actually. So we have something like that, something like that. We could do the dotted lines to make it look a little better. So there's my cylinder. So I think you can imagine it. That one's not hard to imagine. So now I just need to get some points. And since it's not a line, I'm going to need more than 1 point. The other one got really big really fast, so that's why we only did 2 points. This one we're going to do a few more. So it says start at 0. So t equals 0. That gets, okay, r of 0. So cosine of 0 is a 1, times 2 is 2. Sine of 0 is 0, and then 0 there. So I'm going to plot that point. That's right here. Okay, then we're going to do t equals, okay, we want to plug things in that are going to make sense. If I do a 1 or a 2, we're going to have bad decimals with our cosines and sines. So the next value that would make sense, especially, you can imagine, we're probably going to go circular here. Let's choose pi over 2. All right, plugging that in, cosine of pi over 2 is 0. Sine of pi over 2 is 1, times 4 is 4, and then we have a pi over 2. So we go 0, 4, that's out to the right here, and then pi over 2 up. Okay, pi is about 3, divided by 2 is about a 1, so I'm going to go up to what looks like a little less than 2. So we get something like this. All right, still kind of hard to tell what's going to happen. Maybe some of you guys are guessing. We could do t equals pi now. I'm going to jump to the other side of our unit circle. So we got 2 cosine of, okay, pi is negative 1, so it's going to be a negative 2. Sine of pi is 0, and then plugging a pi in there, we have that. That's going to be double the height. So double the height, and then it's going to be negative 2 in the x, 0. So it's over here, but it's just got to be lifted up double the height. So something like that, right? And we have a dotted line because that's on the other side of that side. All right. Then we have a t equals, get off my dotted line, t equals 2 pi. We probably can see enough from this. 2 pi, that's all the way around. Plugging that in, we should get the same thing that we got up there when we plugged in 0. We get 2, 0, and then we get, not 0 though, we get 2 pi. So it doubles the height again, but now we're all the way back around. So if we double that, it's like here. So we get this like, I'm going to put this right here. Let's put it right here, actually. All right, so I'm going to run the rest of that dotted line around. It's like, It goes that way, and then, as you probably can guess, it's like wrapping itself around this tub. This, not tub, but cylinder. So it would just keep going on and on, continually wrapping itself around the cylinder, increasing, it looks like, by units of pi, if we increase time by units of pi. So it looks like it's going to go up with every t equals is 1. We know that for sure from here. So every t that goes past, the spiral will go up 1 more. Pretty neat stuff. The problem is if you don't have stuff from, I think it was 11.6 down, this stuff's going to be a challenge. So it does build on each other. All right. All right, let's take another look at another example of graphing a vector valued function in 3 space. The first thing we always do is write out our components. All right. This one's a bit different. We don't really want to go maybe the square route. We could. Let's go the square route. So we'll go cosine t is x over t, and then sine over t is y over t. And then just like every time with parametric equations, when we're trying to figure out what they maybe look like, is we relate them in some way. So I have sine squared plus cosine squared of t equals 1. I'm going to flip those just because that's where they were. So I square both of those, top and bottom, and I get 1. And right away, you're thinking, okay, maybe an ellipse or a circle, but we have that t squared. Well, we need to get rid of the t squared. That's another variable. But we have this, t equals z. So I'm going to replace, well, first let's do something else. I'm going to multiply both sides by t squared. So we have that. Now I'm going to replace with a z. So x squared plus y squared equals z squared. If we subtract that over, we get x squared plus y squared minus z squared, right? And this tells us, and maybe you don't remember, oh, we have this is equal to 0. This is a cone along z. All right, so to get a sketch of this, I'm going to make it nice and easy, and what this is going to look like, just for the sake of, we've already graphed a bunch of these. Here's a cone, so let's make a cone here. So draw you a cone. I'm going to do, that's dumb anyway, I don't know why I was spending so much time on that. There we go, and we have an ellipse type thing here, and there's our ice cream cone. I think we're all okay drawing that, probably from drawing ice cream cones. I was a little artist as a kid, so definitely did that. You would think I'd be better drawing now. So this cone, what it's going to do when I'm going to put it on the graph, we're just going to think about it. It's going to wrap just like that other one did just a second ago. It's going to wrap itself around this cone. Right, and you can tell my drawing skills are so good, right? So, supposed to be going around the cone. You could probably do a lot better than I did. I can't go forward with my mistakes there, so I'll just redraw it. So there's this cone with that wrapped around it. So that's what it would be. It'd be right in the middle, right? Right smack where this is at the origin. Just erasing everything. This is at the origin here. All right, so there's that example. This is the graphing these vector value functions. It's good to know that they are space curves, and what we mean by that is like almost a roller coaster or a highway in space. Like it's an actual, just a line that curls, not a straight line, that goes through space. That is our vector value functions, and that's what it gives us. Typically, it lives on a surface, unless it's a line. All right, so we're going to do our first little bit of calculus here. So our first bit of calculus, we are going to work on limits on vectored value functions. These are great. The good thing about this, and it's going to be a bit different later with rules and stuff, once we deal with functions of 3 variables, we'll start learning new rules. But for vector value functions, what's great about this is actually, I can just break this down to the limit of x of t as t goes to a. I can let that be my whole I component. Then I can take the same thing, the limit as t approaches a of y of t, and that's j, and then you probably can guess it, limit as t approaches a of z of t, k. So what that's saying is when I'm doing limits, just take the limits to every bit, to every component. It's nothing more than that. So I like to do them off to like by themselves. What I mean like this is the limit as t approaches 2 of square root of t. And the reason I do this is sometimes we're going to be using limit rules and writing this out 4 times to just evaluate one little limit. We're not going to want to do that. So I like going off to the side, working it out, and then putting it back in. Right? Remember, for limits, if we can plug it in, we do. So if we plug in 2 there, we get the square root of 2. All right, let's take our other limit. Limit as t approaches 2, and make sure you're writing limit and everything. You guys made it well past Calc 1. Please do not make me count off because you can't write limit every time you write an equal sign before you take the limit. So, for instance, from here, I did not take the limit. So I'm going to rewrite the limit. What I'm going to do now, this is an old technique from Calc 1, is we factor t plus 2, t minus 2. And we have t minus 2. Oh, forgot to mention, which we should have tried in the begin with, is you always just try to plug it in first. If you try to plug the 2 into this limit, it doesn't work. You divide by 0. So that's why we're looking for something else. I still haven't taken the limit, so please do not be lazy. I will count off. T plus 2 left. Now the limit goes away. I can quit writing limit. It is 4. All right, now I do the last one. Limit of, as t approaches 2, of t over t squared plus 1. We always first check to see, can we just plug it in? I can plug in 2. I can plug it in the bottom as well to get a 5. So the answer to this is square root of 2i plus 4j plus 2/5 k. Oops, that's definitely not a 5. 2/5 k. There we go. So it's nothing new. As long as you can do limits in Calc 1, you'd be able to do limits here. If you weren't great at limits in Calc 1, this is your chance to get better at them. Also, there's this thing as you go through math classes, you actually do something, your brain matures mathematically. Meaning, and you probably have seen this before, if you guys now at this point go back and look at algebra topics, there's something that's going to come up later, completing the square. I think I did a few in the videos, but that's a topic that when I explain how to do it to some of my students, they're like, wow, I've never understood. And now they do. Or logarithms, for instance, when I have people for pre-calc and they've had it in high school. In high school, it didn't mean anything to them. They were better when they got older because their brain developed mathematically. You got better at critical thinking. So please do not go into this with whatever you left Calc 1 with, your idea of limits. Give yourself another shot. Right? They're not too bad. I know for me, when I first went through limits, I was like, I made it through that. I don't really feel like I understand, but when I went back and looked, I was like, oh, this actually does make sense. I think I was just freaking out at the moment because we were so worried about our grades. I work that way anyway with my grades. And the more I slow down and go back and look at things, the better. I'll get off my rant here. All right, so this example, we have another limit, and like I said, we just take this, each one separately, so we can write all the calculus appropriately. So cosine of 0 is 1, so that's great. Now the limit as t approaches 0 from the right of tangent t over t. Now if I try to plug 0 in, tangent of 0, 0, t is 0, I get 0 over 0. That is the indeterminate form. That calls for L'Hopital's rule. This is what I used to signify that I used it. Whatever you have, I'll be able to pick it up when I'm grading your stuff if you use L'Hopital's rule, if you use it correctly. Remember, it has to be a 0 over 0, infinity over infinity. It has to be indeterminate. So the derivative tangent, hopefully you remember that. That's secant squared. and then I get a 1. Now I'm going to rewrite this, though, because I don't know secant. Just my brain doesn't work with secant, cosecant, and cotangent. I have the other stuff down. So I'm going to think 1 over cosine squared of t. Now I can plug that in because cosine of 0 is 1. 1 squared is 1. We get an answer of 1 here. All right, now we can do our last limit, the limit as t approaches 0 of t ln of t. All right, this is the reason I'm showing you this one. There's a trick here. The limit as t approaches 0. Now, I can't do even though like plugging in 0 and then ln, I can't even plug in 0. So we have an issue right away. But we get an indeterminate form if we rework it like this, ln of t, and then I'm going to put 1 over t. I want you to stop and think about that for a moment and why that's legal. Now, I can't plug them into both, so I can use L'Hopital's rule. So L'Hopital says as t approaches infinity, I can just take the derivative 1 over t, and then down there I got 1 over negative 1. Negative 1 over t squared is the derivative of 1 over t. I'm going to flip things over, still have my limit. Okay, I get negative t. I can plug in 0 there and get 0. If you were just to write equal 0 at the very beginning, you wouldn't get any. I give you credit for getting the answer, and it's usually like a fifth of the points, if that. So without this work here in the middle, you're not going to get credit for that. You'll get my sympathy credit to not give you a 0. So you have to have some kind of, if you have another technique for that, there's some other techniques for that. Kudos, do it. Okay, so we're there. Now we have an answer to this. The answer is I plus j, right? 1i plus 1j. There's no k. You could put plus 0k if you wanted to. That's fine. It's not wrong. We just don't typically do it. All right, we're going to determine a couple more examples, one more topic, continuity. Continuity for this stuff, for vectored value functions, will come down to just find the domain of that function with what we're dealing with anyway, because it's not going to get super complicated. They could make it in a way where we would have to consider more than this, but if I think of the domain of everything, I can't plug 0 into this, so t can't be 0. Okay, t also can't be, okay, the numerator's okay. Here, t can't be, if I think about solving that, negative 1/2, and then t can't be 0. So the domain here, oh, and then we also have this square root of t up here. Has to be greater than or equal to 0. So we go to restrictions. Okay, so this tells me everything has to be 0 or positive. All right, so that just kills that. And it can't be 0, so it's going to have to be t is greater than 0. Or 0 to infinity is what we prefer. And then it's continuous on with vectored value functions. It's safe to do this. Continuous on that. Okay, so all we're looking for is a domain. So for this first one, t can't be plus or minus 2. Arc sine, if we think about the domain of sine, that's the going to be the domain for this, or the range of sine, rather. Range of sine is the domain of this thing. That's an algebra pre-calc topic. Sine lives between -1 and 1, so it's restricted between there if I'm going backwards. And then this last one actually can just be anything because it's a cube root. I can take cube root of negatives. So the restricted here, the most restricted, is that middle. So it's continuous on -1 to 1. And that's it. I won't ask too many of these, but it's important to know because we're going to do calculus on this, including derivatives and integration.